end behavior.
Okay.
And increasing and decreasing intervals.
Okay. Getting into calculus. Okay. What do you got?
I don't know.
What do you got for a function?
Fx equals, oh, hang on, that's not what I wanted it to be. Hang on, okay. I mean, she just gave us a graph and she said, find the end behavior.
Ah, okay. So she gave you a graph instead of a function. All right.
Yeah.
End behavior is what happens to f of x as x goes to infinity or minus infinity. In other words, if, let's say I gave you the graph like this, and I didn't tell you what the function was, what happens to f of x as x goes to positive infinity?
Y goes to positive infinity?
Now look at the graph. Look at the horizontal axis. If we're going in this direction, which is what happens when x goes to infinity, what happens to f of x on the graph?
It goes to negative infinity?
No, it goes to 0.
Okay.
Can you see why?
No.
Well, this is f of x. Okay, if I say what is x, that's f of x. Okay, so as I move to the right, f of x is getting smaller, 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 smaller. It's approaching this line y equals 0. You with me?
Yep.
As the other end behavior is what happens when x goes to negative infinity. In other words, what happens when we go that direction to the max? Well, what happens to f of x as we go to negative infinity?
Goes to 0?
Again, exactly. Goes to 0 from the negative side, but it still goes to 0. And this function happens to be y equals 1 over x. So you can see that as x goes to positive infinity, y is going to go to 0. And as x goes to negative infinity, y is going to go to 0.
Okay.
Okay. Now,
So
end behavior might be the one thing I can do without seeing the chart. Most of the time, if you need me to interpret a graph, you need to take a picture of it and send it to me.
okay.
Okay? That's the easiest way. End behavior is pretty straightforward. In other words, no matter what the graph looks like, it's what happens as x goes to positive infinity or what happens as x goes to negative infinity. That's what end behavior is all about. Let's say I had this graph. Hyperbolic again. I know there's a vertical asymptote at x equal 1. And this graph looks like this. So what happens, remember y and f of x are the same thing. Okay? Don't get confused by when they give you f of x sometimes and they give you y sometimes. It's just the same notation. I mean, it's different notation for the same thing. Well, here, what happens in my picture that I just drew, what happens as x goes to positive infinity?
y gets closer to 0.
And what happens as x goes to negative infinity?
Y goes to 0.
Right.
So how would I write that?
Huh?
How would I write that?
Well, end behavior, the definition of end behavior is what happens to y as x goes to positive infinity. So y, the limit of y is 0 as x goes to positive infinity. So technically that's the way to write it. Okay, also the limit of y, or f of x, equals 0 as x goes to negative infinity. Are you familiar with that notation? Have they introduced that to you yet?
Not really.
Okay, but you're getting close because they're talking about end behavior. And that's what end behavior means. Now, there's something else that happens that end behavior means. And if you have horizontal asymptotes, let's say I have an asymptote right there, and I have another one right there, and I have a logistic function that looks something like that. What happens to f of x as x goes to positive infinity?
It goes to 5.
Okay, that's the right-hand end behavior. What happens to f of x as x goes to negative infinity?
Goes to 2.
That's the left-hand end behavior.
I think what she's looking for is cubic functions and finding the and
If you have a problem that you can verbalize to me, it'll be easier for you to describe it.
okay, I found one. Y equals x cubed plus 5x squared minus 9x minus 45.
That's it?
Yeah, that's it.
Okay. End behavior is a function of one thing and one thing only, and that's the highest degree polynomial. Okay?
Okay.
I can ignore those three things. They have nothing to do with end behavior. End behavior is always controlled if you have a polynomial like this. End behavior is always measured by the highest degree polynomial. So, in other words, this end behavior is exactly the same as this. Well, what happens to y as x goes to positive infinity?
Goes to positive infinity.
Yeah, here's what my graph looks like. That's y equal x cubed. What happens to y as x goes to negative infinity?
Goes to negative infinity.
There's your two end behaviors for this function. You can ignore everything other than the highest degree polynomial in regards to end behavior. Nothing else makes a difference. Only the highest degree matters.
So if I have a polynomial like y equals negative 2x to the fifth plus x to the fourth plus x cubed plus x squared.
That's the highest one right there.
No, it's x to the fifth minus 2x to the fifth.
And didn't you say plus x to the fourth?
No.
Oh, excuse me. What was it?
No.
It was minus 2x to the third,
The fifth.
and that's the highest degree?
Yeah.
Okay. What happens as x goes to positive infinity? What does y do?
Goes to positive infinity.
No, goes to negative infinity. In other
Why?
words, well, because if I were to graph this, that is a reflection, basically, of that over the x-axis. Okay? Well, when I reflect this over the x-axis, I get something that looks like that.
Okay.
Now you can see that as I go in this direction, as x goes to positive infinity, y goes to negative infinity.
Okay.
If you can't see that, tell me, because that's a really, really important concept to understand.
No, I understand.
Okay, and if we go in this direction, what happens to y?
Goes to positive infinity.
Exactly. So that's all in behavior is talking about, is what happens to either y or f of x as x goes to either positive infinity or negative infinity. And you can have curves that look, how about this curve here? That's y equal x squared. What happens as x goes to positive infinity?
X goes to positive infinity. Y goes to positive infinity.
And what happens as x goes to negative infinity?
Y goes to negative. Y goes to positive infinity.
Exactly. Y still goes to positive infinity. So that's all you care about is what's happening to y as we go to the right or as we go to the left on the x-axis.
So is there a pattern to these or something?
Well, the pattern is the only part of the polynomial you care about is the leading degree. In other words, I can have a very complex polynomial, and it doesn't matter what else comes. In other words, I can have an x to the fourth, an x to the third, an x squared, an x. None of it matters. The only thing that matters is what happens as x goes to positive infinity.
Okay.
What happens here?
It goes.
What does y do? The way to solve these is just to stick in infinity. I mean, I know they don't like to do this in class, but if you did it, that's still positive infinity. But now I'm multiplying it by a negative, so that's negative infinity.
Okay.
Okay? But that's the way to answer the question. It's just substitute the infinity letter in there and then figure out what happens to it. If you multiply positive infinity by a negative number, it's negative infinity. That's why when you have that leading negative, it reflects everything over the x-axis. And that's what makes y go to negative infinity and not positive infinity.
Okay. I have.
And it's important to understand that that's the definition of a horizontal asymptote. If I have a horizontal asymptote up there, and whether I have a vertical asymptote or not, the definition of horizontal asymptote is what does f of x go to as x goes to infinity? Well, I might have this set of asymptotes, and this kind of curve, what happens as x goes to positive infinity?
Y goes to 3.
What happens as x goes to negative infinity?
Y goes to 3.
Yeah, and it's possible sometimes that you can cross horizontal asymptotes. In other words, this curve could look like this. That's okay. Doesn't matter. It's still as x goes to negative infinity, y goes to 3.
Okay.
Okay.
So there's one more thing I wanted to work on, and that was
I'm having a hard time understanding what you're saying, Julie.
I'm looking for relative maximums and minimums.
Okay.
Given equations.
At the Algebra 2 level, usually they're only going to ask you maximums and minimums on second-degree polynomials. In other words, if I have a parabola, that's a quadratic. The minimum always occurs right there. If I have a parabola that's this way, there's a maximum that always occurs right there. Both of those occur at the vertex. So if you can figure out where the vertex comes, that's where the minimum and maximum come on quadratics, second-degree polynomials. Sometimes, if you get into higher degree polynomials, let's say a cubic that looks something like that, well, now in this range, we have a local maximum, and we also have a local minimum. But only if I'm referring to a very narrow range. Actually, I didn't draw the right-hand boundary properly. In other words, if I was referring to that range, from where x goes from there to there, there is a local maximum in that range, and there is a local minimum in that range. And that's what they're talking about when they talk about maximums and minimums. And this is very useful because you might have a function that looks like this, and you want to know where the maximum of that function is on the x-axis. In other words, I want to know what value right there produces a maximum of that function. Maybe my function is the size of an open box, the volume of an open box. Well, the volume of an open box is base times width times height, but if I want to know what to make each of those to make the volume the maximum, I want to study the volume function. That's the volume function. Okay, and so I would know that the maximum volume of a box, if this was its function, would be right there. Well, you say, well, how come it's not right there? Well, within a certain range, this is the maximum function. In other words, if I restrict my range from 0 to, say, 5, well, the maximum of that function occurs right there, let's say 2. Okay, so that's conceptually maximum and minimum. It's easier to work these problems if you have specific problems. I mean, it's easier to gain the understanding of what's going on if you can give me a specific problem rather than just explaining.
A specific problem.
Okay, cool.
Y equals negative 6x to the 5th plus 14x squared plus 20.
Okay, and what's the question?
Find the relative maximums and minimums Write the increasing and decreasing intervals and find the real solutions.
Okay, we allowed to use calculator?
Yes.
Okay, let me pull this up on my Wolfram Alpha, and we'll take a look at it, and then we can answer all those problems. Minus 6x to the fifth, hold on a second. It's minus 6x raised to the fifth plus 14x squared plus 14x raised to the second plus
20.
20 or 40, it's not going to matter. 40?
20.
All right. This is what that function looks like. And the nice thing about Wolfram Alpha is they tell us what I typed in, which is very useful. They don't do that on a TI-84. You can type that into a TI-84 and get it wrong, and they won't tell you. But they do tell you on this. And so this gives you two charts. One is zoomed out, one is zoomed in. Okay? Well, on the zoomed in chart, this one up here, we can clearly see that we have a maximum at about 1. Right?
Mm-hmm.
If we look at the zoomed out chart, well, the maximum, as long as we go to the left of -1, is above that. So this is called a local maximum. In other words, that's only a maximum if you're looking at between 0 or x greater than 0. For x greater than 0, that is a local maximum. Now, Wolfram Alpha also gives you some other interesting numbers. They give you the real 0. Notice that the real 0 occurs right there. That's at 1.6759. And then there's 4 imaginary zeros. And we would expect that because we're looking at a 5th degree polynomial. When you have a 5th degree polynomial, you expect 5 solutions. Okay? But only the real solutions cross the x-axis. Well, if you look at that, it only crosses the x-axis right there. So all the other 4 solutions, which it's giving us here, are all imaginary. And when you have imaginary solutions to a polynomial, they don't cross the x-axis. Okay, if I give you this polynomial, that's y equals x squared plus 3. Notice that it does not cross the x-axis. What that tells me is this only has complex solutions, 2 of them. There's no real solutions to this. In other words, there are no real zeros because if you take a number and square it and then you add a positive number to it, you're only going to get positive numbers. You can't get a 0. There's no way to make y equals 0. So it's useful to know that you only get zeros with positive or with real solutions, not with imaginary ones. Okay, so in this problem, we have a 5th degree equation. We would expect 5 solutions, and indeed we have 5. We have 1 real solution, and we have 4 imaginary solutions. So what did they want to know? They wanted to know where it was increasing also?
Mm-hmm.
Okay. Well, if we look at this function right here, it's clearly not increasing from here down to here. That's decreasing, right?
Mm-hmm.
Well, if we look at this part of the graph, closer, right here, we can see that it appears to be increasing from 0 to 1. And indeed it is, I suspect, increasing from 0 to 1 precisely. And then it's decreasing from 1 to infinity. Or actually, it's decreasing from negative infinity to 0, and then it's decreasing from 1 to positive infinity. And the only place it's increasing appears to be from 0 to 1. What else did they ask about this function?
Relative minimum and maximum.
Over a certain interval or absolute? In other words, there's a difference when you talk about minimums and maximums. There's absolute minimum and absolute maximum, and then there's locally. If we look at the zoomed out chart, we can see that there is no absolute maximum. The absolute maximum is infinity. It doesn't show it, but if I go far enough to the left, this function will keep going to positive infinity, right?
Yeah.
And if I go far enough to the right, my end, in other words, my end behavior for this function is positive infinity on the left, negative infinity on the right. So if I'm talking about absolute maximums, it's infinity. If I'm talking about absolute minimums, it's negative infinity. Now, if I'm talking about absolute maximums on an interval, in other words, if I'm talking about the interval from 0 to 1.5, well, then there is a local, it's called a local maximum that occurs right there, and I'm guessing that has to be x equal 1. And in the interval from 0 to 1.5, there is a local maximum at x equal 1. But it's only local. In other words, it's not an absolute maximum. It's a local maximum. You understand the difference between absolute and local?
Yes.
Okay. Let's see what else this thing tells us. What other questions did they have for you on this function?
Not much else.
Okay. But you'll notice that Wolfram Alpha does a great job with functions. In other words, they tell you what you put in. They give you a zoomed out and a zoomed in look at it. They also tell you the zeros. In other words, if the question was find the zero of this function, you'd have to use your calculator and go in there with the trace button. But with Wolfram Alpha, they give you the zero. It's 1.6759. That's what that value is right there. Okay? It's probably an irrational number, and they've rounded it off. They even plot the complex roots. Notice that they give you the imaginary part of it and the real part of it. In other words, when you plot complex numbers, that the horizontal axis is the real, the vertical axis is the imaginary part. They give you the first derivative of it, which is a calculus. They give you the integral of it, which is a calculus. And they do actually calculate the local maximum. Notice that it wasn't 1. It's the cube root of 14/15, which is as close to 1 as you can get, but it's not exactly 1. If I go up here and I put my cursor on that, whatever that maximum is, it's slightly less than 1. It's the cube root of 14/15, according to Wolfram Alpha. And that certainly agrees with the graph that we're looking at. It appears to be very, very close to 1. It's not precisely 1. All right. Good to go, Julie?
Yeah.
I will talk to you next Monday.
Okay.
All right, bye-bye.
Bye.